In this podcast, we'll demonstrate how to use methods of calculus to graph the function y equals x squared e to the x, showing intervals over which it's increasing and decreasing, intervals over which it's concave up or concave down, and the locations of any points of inflection or asymptotes or maximum and minimum values. So the first thing we'll need to do is to get the first and second derivatives, and this being a product, we'll begin with the product rule. So we will have x squared times the derivative of e to the x plus e to the x times the derivative of x squared, and we can factor out an e to the x, leaving x squared plus 2x. And looking ahead to when we'll want to know zeros, we can further factor this quadratic into e to the x times x plus 2. If we then go again, second derivative, probably best to go back to this line where we have only two factors rather than this line where the double product rule gets pretty complicated. So we will have e to the x times the derivative of x squared plus 2x plus x squared plus 2x times the derivative of e to the x. If we factor out the e to the x and collect some like terms, we will have e to the x quantity x squared plus 4x plus 2. Having found the derivatives we need, we then need to analyze when the function, the first derivative, and the second derivative are 0 or undefined or positive or negative. And if we begin with the function itself, it is of course 0 at x equals 0 and positive elsewhere. If we then look at the first derivative, it will be 0 at 0 and at negative 2. And you can test intervals, or you can recognize that e to the x is always positive and the remainder is a quadratic opening up, and that would indicate this configuration of signs. And finally, we need to know values for the zeros of this quadratic, and if you use the quadratic formula, you'll find that they're at about negative 3.4 and about negative 0.6. So maybe about here and about here. And this is also a quadratic opening up, and so we will have then this configuration of signs. We can then use the sign charts to identify key features of the graph. So if we look at the first derivative, y prime, we find a change from positive to negative at negative 2. That tells us we'll have here a local maximum, and a change from negative to positive at 0. That tells us we'll have a local minimum. And in looking at the second derivative, we find that these sign changes will correspond to inflection points. We now can begin to set up our axes with these values in mind. So we might want to go something like this off to the left, out to about negative 4. And we'll complete things a little ways off to the right. We're not so much interested in the heights of things. We can always calculate those if we want by plugging the appropriate x values into the function. But this is supposedly a quick sketch. So we'll begin by locating the origin as being on the graph. And if we then look to the right, we find really nothing changes to the right of 0. So we have a function that is positive, increasing, and concave up, and we know certainly from the expression that this is going to grow pretty explosively. So something like that. We know then also from negative 2 to 0, the function was decreasing, concave up out to about negative 0.6, which is maybe about here, and then concave down until a maximum at x equals negative 2. So try and make it look like the inflection is changing there, something like that. And then to the left of -2, we're increasing, concave down out to -3.4, and then concave up thereafter. And it's worth now looking at the end behavior of this function as well. For large negative x's, the x squared is going to be a big positive number. The e to the x is going to be a tiny number. And as you may know, the exponential is going to win out over the power, so we're going to be asymptotic to the x-axis out to the left. And that pretty much gives us everything we need to know. We just need to finish our max here, get out to about -3.4, switch our concavity, and then head out to the left. And there is our graph of y equals x squared e to the x.